time I started introducing the notion of spectrum. It's a very important notion in solving differential equations, integral equations, all kinds of functional equations. Okay. So, let me first go back to what we did last class and recall a bit. Okay. So, what we have is, suppose you have a matrix A which is n cross n complex. So, suppose I have a complex n cross n matrix, then this automatically generates a linear transformation on n component vectors mapping x to A x. So, we have a map, we have a mapping or a transformation A mapping C n to C n defined as x in C n mapped to A x in C n. Obviously, if x is in C n and A is an n by n matrix, A x will also be in C n. So, it defines a matrix, defines a linear and is obviously linear because matrix multiplication is linear. Okay. So, therefore, A is a linear transformation. In fact, it is a linear operator because it transforms C n to itself. So, I have a linear operator, and then we had generally one of the most important notions in matrix theory is the notion of eigenvalues. So, a number lambda in C is called an eigenvalue of A if there exists a vector such that x is not 0, such that A x equal to lambda x, or that is the same thing as saying that is A minus lambda I x is equal to 0. Now, that means something other than the 0 vector goes to the 0 vector under the transformation A minus lambda I, which simply means A minus lambda I is not 1 1. That is, if A minus lambda I is not 1 1. But if A minus lambda is not 1 1, automatically the inverse is not defined. So, therefore, that is A minus, therefore, A minus lambda I is not defined, inverse. So, if lambda is an eigenvalue, A minus lambda I is not, inverse is not defined. The moment lambda is not an eigenvalue, then A minus lambda I is 1 1, and if you have finite dimensional space and there is a linear operator on that, then rank nullity theorem says if rank plus nullity is n, if it is 1 1, nullity is 0, so rank is n, and so it is onto also, so the inverse is defined. Okay. So, if lambda is not an eigenvalue, okay, let me put it. The lambda is not an eigenvalue implies A minus lambda I x is equal to theta n, if and only if x equal to theta n. That implies lambda A minus lambda I is 1 1, and therefore, onto by rank nullity theorem, and therefore, A minus lambda I inverse exists. Okay. So, the only time, the only values of lambda where we have problem of defining this A minus lambda I inverse are the eigenvalues of lambda. Okay. So, hence A minus lambda I inverse is defined if lambda is not an eigenvalue of A. What we wanted to look at was lift this whole thing up into infinite dimensional spaces and also lift it to the non-linear spaces, and therefore, wherein we not only want A minus lambda I inverse, but we also want it to be a bounded inverse. So, now we go generalize. Suppose X is a Banach space. I will work only with Banach spaces, otherwise it becomes more and more messy. So, let us say it is a Banach space and F mapping X to X a bounded linear operator on X. So, I have a bounded linear operator on X. I want to look, we want to look at those lambdas, again, well, let us take complex Banach space, the scalar inverse are complex numbers. So, then I want to look at all those lambdas for which F minus lambda I inverse. So, the role of the matrix is now played by this operator F. F minus lambda I inverse cannot be defined as a bounded linear operator. We will see some examples later. First, let us get the formal definitions properly out of the way. Okay. So, now let us see what are all the situations that may force difficulty in defining F minus lambda I inverse. So, for convenience, so let us denote, instead of writing F minus lambda I, let us denote F lambda to be F minus lambda I, so that I do not have to write all the time F minus lambda I. Okay, so let us denote by F lambda F minus lambda I. So, we want to look at all those points, all those complex numbers such that F lambda inverse does not exist as a bounded operator. This is the lambdas that we want to look at. This is called all these values of lambda, which are complex numbers, set to form the spectrum of the operator F. So, this is denoted by sigma F and called the spectrum of the operator F. And anything outside this sigma F are those lambdas for which I can define F minus lambda I inverse. They are called those lambdas set to form the resolvent set. So, I will call it as RF. Okay, I will use some other notation. I will use rho F to be all the remaining complex numbers, that is those lambda in C such that F lambda inverse exists as a bounded operator. That is called the resolvent set of F lambda of F. Okay. So, the complex numbers have been split into two parts, one the spectrum and the other the resolvent. Okay. So, therefore, we are interested in numbers lambda for which f lambda inverse creates problems. So, let us look at what are all the cases where there will be problems. Okay. So, let us look at lambda belonging to C. One way that the inverse not exist if the operator f lambda is not even 1 1, then there is no chance of defining an inverse. So, 1 if f lambda is not 1 1, then clearly we cannot even define f lambda inverse, leave alone boundedness. So, even to get to boundedness, first it must be defined. We can't even define f lambda inverse. So, that is the first set of points that may belong to sigma f. Then all such lambda belong to sigma f, the spectrum. Okay, so that is one. The next set of points are those for which now they are away from this. So, for which f lambda is 1 1. So, these are f lambda is 1 1. Now, f lambda is 1 1, f is bounded, I is bounded, therefore, f minus lambda is bounded, and therefore, I have a bounded transfer operator which is 1 1. If by chance it is onto, then open mapping theorem and the boundedness inverse theorem will tell f lambda inverse is bounded. So, if f lambda is also onto, then by bounded inverse theorem, which is a consequence of the open open mapping theorem, f lambda inverse is bounded. So, all these lambda cannot belong to sigma f. So, all these lambda will belong to rho f. So, all these lambda belong to rho f, because in that case I am able to define f lambda inverse as a bounded inverse. So, now look at 3. F lambda is 1 1, but f lambda is not onto. That is the case where we are left out 1 1, not 1 1, 1 1 and onto, but now we have to look at 1 1, but not onto. So, f lambda is 1 1, but not onto. We will investigate this case. There are some peculiarities that take place here. Okay, unlike in infinite, just if you add vector spaces, things are different, but now this boundedness makes a little bit more inroads into it. Okay. So, now let us look at what is going to happen. So, what does that mean? Here I have the vectors, the norm linear space, and then f is taking mapping from here to f lambda is mapping from x to x. If it is not onto, what it means is that the range is not the whole space. So, it will be part of it. So, the range of f lambda, which I will call as R f lambda, it will not be filling up the whole space, there will be some gap. Okay, that is what is meant by not onto. So, hence range of f lambda, which we denote by RF lambda is a proper subset of X. Okay. So, now look at the part, we want to come back from here to here, that is what is meant by saying inverse. Now, for coming back from here to here, in this part I can certainly define inverse, because f lambda is a mapping from X to RF lambda 1 1 and on to now, and therefore, the inverse can be defined. Okay. So, clearly f lambda viewed as a transformation f lambda to X to RF, the same metric to that makes it a RF lambda, makes it a nonlinear space, is a 1 1 onto linear transformation. Okay. That is for clear. It is 1 1 because f lambda is a 1 1 all the time. Now, we are getting on to, because we are restricting ourselves only to place where f lambda goes, that is the range of f lambda, and therefore, we are able to define the inverse. Whether it is bounded or not, that is a different question, we will investigate later. In order to define the bounded inverse, first of all you must define the inverse and then worry whether it is bounded or not. So, therefore, at least hence we can at least define f lambda inverse as a linear transformation from R f lambda to X. So, I have this inside, this is, I will just take R f lambda to X, and now I have f lambda inverse, that is well defined. From the range of f lambda I can pull back, because something is in the range of f lambda means that fellow is f lambda of X, and therefore, the inverse will be the X. Okay. So, therefore, there is no problem about defining the inverse on the range of f lambda. Now, let us forget, okay, our ambitious project is define f lambda in the whole space, but at least now we are able to define the inverse there. At least is it bounded there? That I do not know. At least this partial inverse that we have got, is it bounded? Okay. So, it may happen that this partial inverse is bounded or not bounded. If it is not bounded, so if the partial inverse is itself not bounded, how are you going to get the whole inverse as bounded? So, the possibility is that the partial inverse is bounded and not bounded. Suppose, okay, suppose this partial inverse is not bounded, then there is no hope of defining f lambda inverse as a bounded operator. So, let us assume, proceed, okay, this difficulty does not arise, the partial inverse is bounded. Suppose therefore, the partial inverse is bounded. What exactly does this mean? That means this operator that we have defined, this transformation that we have defined from this space to this space is a bounded linear transformation. What does that mean? Bounded means there exists a constant m such that the changed length is less than or equal to m times the original length. Now, where is the original length? Here. So, let me put it as y. Where is the changed length? Here. So, f lambda inverse y. For what? For every y where you started with in the range of f lambda. This is what it means to say that this partial inverse is bounded. The changed length of the partial inverse is always dominated by a constant times the original length of the vector. So, that means it works within an elastic limit within the domain where it is defined. So, it is works within that. This I will call it as 1. This I will use. So, therefore, I have a partial inverse now which is bounded. My aim was to get a bounded linear operator completely inverse, but at least I have got a partial inverse. Now, what can I salvage from that? That is what I am going to look at. So, what is meant by this f lambda inverse which I have defined is linear. Always the inverse is linear, as long as this way it is linear, the inverse will that way will be linear. So, it is a linear bounded. Now, whenever I am talking about linear transformations, boundedness and continuity mean the same thing. So, f lambda inverse is continuous in this part. So, basically what it boils down to saying, if in general if you know a continuous function on the dense set, you know it in the whole space. So, in other words, I can push a continuous, try to push a continuous function to the closure of the whole space. Okay. So, therefore, let us look at this, how we do this. Suppose, so let me, where shall I write? Okay, I will erase this, keep that picture. Okay. Suppose now, see what I am trying to do is, how far can I push this partial inverse? If I can push it all the way up, then I have got the full inverse. So, I am trying to push this partial inverse. I have information only up to this, I am trying to push it outside this. The first step is, suppose y belongs to closure. What does that mean? It is either in that or it is a limit point of that. That means this implies either y is in RF lambda or y is a limit point of RF lambda. The closure is the set together with all the possible limit points. So, suppose I take a limit point of the, suppose I take the closure, then any point in the closure is either in the set or must be a limit point of the set. Now, if it is here, then f lambda inverse y is defined, because it is here and we have already defined the partial inverse. So, therefore, the moment y is in that portion, already we have got the f lambda inverse. The worry is, now what can we do here? If y is a limit point, that means there is a sequence that converges to that. From the range we can now approach that y. So, this means there exists a yn in the range of f lambda such that yn converges to 1. Of course, all the convergence is in the same norm, that norm with respect to that norm. So, if it is a limit point, there must be a sequence which is converging to it. Then you see, I do not know how to define this, but I know how to define the inverse here, because these fellows are all in the range. The moment somebody is here, I know how to define the inverse. So, we know how to define f lambda inverse yn, because yn belong to the range of f lambda. And therefore, since I know f yn goes to y, f lambda inverse I know to define f yn. So, the possible hope is define f lambda inverse y as the limit of f lambda inverse yn. So, probably a natural way of defining f lambda inverse y is f lambda inverse y equal to limit n tend to infinity f lambda inverse yn. This I know, so therefore I can write this. Now, why did I say probably? First, I am not very sure whether the right hand side limit exists. Who told me that I know yn converges to y. How do I know that f lambda inverse yn converges at all? So, I must ascertain that that limit exists. Secondly, even if that limit exists, how do I know that if there is some other sequence Zn which also converges to y, then how do I know that f lambda inverse Zn is not the right definition, or whether both will give the same definition. So, therefore, probably means the following. I wrote probably, there are, because of this there arise two questions. One, I will keep this. I will draw the picture. I will draw the picture later again and again. Okay, the first question is question 1. Does limit n tending to infinity f lambda inverse yn exist in the first place? To make that any sense out of that definition, we must make sure that that limit exists, and if the limit exists, is it independent of the sequence chosen to converge to y? That is, what does that mean? That is, I am running out of space. Okay, now, because of that is, that last part, that is, if Zn converges to y, then is limit n tending to infinity f lambda inverse Zn same as limit n tending to infinity f lambda inverse yn. Then this makes sense, the definition we gave makes sense. Otherwise, remember how I erased this. Okay. So, what is the definition we said? Probably f lambda inverse y we can define as f lambda limit n tending to infinity f lambda inverse yn. Otherwise, different fellows will get different answers, but inverse operator must be properly defined. There cannot be any confusion. So, therefore, these two questions we must settle. If we settle these two questions, then we can define f lambda inverse y not only inside the range of f lambda, but also to the closure. Okay. So, we will now ascertain these two. The question 1, we will answer 1, the answer to the question 1. Okay. Now, we want to show that this limit exists. Well, it is enough if we show that is a Cauchy sequence, because we are working in a Banach space. Any Cauchy sequence in a Banach space will converge. So, it is enough to show So, ETST, enough to show that f lambda inverse yn is a Cauchy sequence because X is a Banach space. So, any Cauchy sequence in a Banach space will converge and we will be happy. Okay, that is right. So, therefore, all we have to show that it is a Cauchy sequence. Now, what should we do to show that something is a Cauchy sequence? The nth term and the mth term, the difference can be made as small as possible, f n and m and large. So, let us estimate that. So, the norm of f lambda inverse yn minus f lambda inverse ym now, where are these yn and ym? Yn and ym are in the range of f lambda and f lambda inverse is linear there. So, that is equal to f lambda inverse yn minus ym. Yn is in the range, ym is the range is a subset, therefore, yn minus ym will also be in the range. So, therefore, this is f lambda inverse of a vector in the range of f lambda. But whenever you take f lambda inverse of a vector in the range of f lambda, the norm will be less than or equal to m times the norm of this. So, this is less than or equal to m times norm yn minus ym by 1. We are done. Now, yn is converging and therefore, yn is Cauchy and therefore, I can make this small. But if I can make this small, I can make this also small. Okay. So, therefore, now I have okay. I will erase question 1. Okay. Since yn converges to y, the sequence yn is Cauchy sequence. Therefore, for every epsilon positive, there exists an n epsilon such that n and m greater than or equal to n epsilon. I can make it as small as I want and I will make it as less than epsilon by m. So, that implies norm f lambda inverse yn minus f lambda inverse ym is less than epsilon, m times epsilon by m is less than epsilon for every n and m greater than epsilon. So, therefore, question 1 is okay. Therefore, f lambda inverse yn is Cauchy. So, question 1 answer is yes, the limit exists. Okay. So, question 1 is disposed of by the simple fact that we have a Cauchy sequence in a Banach space and therefore, it converges. The Cauchiness of f lambda inverse yn came on 2 counts. One, the linearity of f lambda inverse and the boundedness of f lambda inverse on the range of f lambda. That was important and therefore, we are okay with question 1. So, now let us look at question 2. Okay. So, we wanted to show that if there are 2 sequences Zn also converging to y, we wanted to show that the 2 limits are this thing. So, suppose Zn converges to y, yn converges to y and therefore, yn minus Zn converges to the 0 vector. Okay. So, what can you conclude from this? So, now we have f lambda inverse yn minus f lambda inverse Zn that is equal to norm f lambda inverse yn minus Zn because f lambda inverse is, and again yn is in range, Zn is in range, therefore, yn minus Zn is in range and therefore, that is less than or equal to m times yn minus Zn by 1. Now, what happened? since yn minus zn goes to 0, this goes to 0, and therefore this must go to 0, which means f lambda inverse zn limit is the same as this. So, this tends to 0 because yn tends to zn. Therefore, limit f lambda inverse yn is indeed equal to limit f lambda inverse zn. Okay. So, we have made some progress. We now know, first we can define the inverse from the range, and if that inverse is bounded in the range, we have a slight hope of pushing it a little further to the range of f lambda. So, what is the conclusion? So, the conclusion therefore is, let us now write all the conclusion. If the partial inverse f lambda inverse defined on range of f lambda is bounded, then we can extend it to RF lambda closure. But when you extend that, it will lose boundedness, because some new fellows have come. There has the elasticity been affected. Will that be affected? Because norm limits are maintained, norm of f lambda inverse yn will be less than or equal to m times norm yn, and therefore the limit will also maintain. Therefore, f lambda inverse y will also be less than or equal to m times Laplace. So, and this extension is also bounded. So, therefore, we have got a little bit progress. We are able to define the inverse on the range of f lambda closure, and if that range of f lambda closure is all of the space, we are done. We have got the inverse in the whole space. So, if range of f lambda closure is all of x, when does that happen? If the range of f lambda is dense. If it is dense, its closure will be the whole space, everybody can be approximated. That is, if range of f lambda is dense in x, then we have f lambda inverse defined on all of x as a bounded operator. So, let us again make another conclusion. Okay. So, we will call it as 3a. f lambda is 1 1, not on 2, but range of f lambda is dense and f lambda inverse is bounded on range of f lambda, then f lambda inverse exists as a bounded linear operator, because these two conditions says I can extend to closure, and because it is dense, its closure is the whole space, and therefore, all such points will not be in the spectrum, they will be in the resolvent set, because we are able to decide. So, all such lambda belong to resolvent. Now, this is a special case of that, because when the range, when it is onto, the range is the whole space. So, obviously it is dense. Okay, and this makes it bounded also, because the 1 1 and R2, the open mapping theorem, it is bounded. So, it is dense and bounded. So, this is another way of stating that part is also included in this. So, this is this can also be in this, it is bounded, it is dense, everything. So, therefore, I will not write 2 because 2 is subsumed by 3a. So, therefore, what is the other part where this does not happen? So, 3b is f lambda is 1 1 not on 2, but RF lambda is dense and f lambda inverse is not bounded on RF lambda, right. These are the two cases. Dense, f lambda inverse is bounded, f lambda inverse is not bounded. Now, if f lambda inverse is not bounded even in the smaller piece, there is no hope of defining it as a bounded operator on the whole space. Therefore, all these lambda belong to spectrum of F. Now, the last case is, now both these cases are the cases where the RF lambda is dense. So, in the first case, the RF lambda itself is not dense, there is no hope of going all over the place, because you have a lot of uncovered region. Lambda belonging to C such that RF lambda is not dense. All these lambda belong to spectrum of F. Okay. So, the spectrum of F has 3 parts. 1, this, where it is not 1 1. 2, where it is 1 1, okay, but F lambda 1 1, but RF lambda is not dense. This is 2 and this is 3. Anything else will belong to resolvent. Okay. So, the spectrum is divided into 3 parts, whereas in the matrix case this was the only part, everything else automatically vanished, there is nothing there. But in general, if you are working in a general Banach spaces, the spectrum will consist of generally 3 possible parts. Some of them may be empty, but in general there are 3 possible parts. 1, where it is not 1 1, f lambda is not 1 1. 2, where f lambda is 1 1, but the range is not dense. 3, where the f lambda is 1 1, range is dense, but the inverse is not bounded on the range. Okay. And in all other cases, the f lambda inverse exists. Okay. So, therefore, the spectrum, and see the 3 parts are disjoint. This part is different from this part, is different from this part. So, these are 3 disjoint pieces in the spectrum. So, hence the conclusion is let f mapping x to x be a bounded linear operator on a Banach space then the spectrum of F consists of 3 different pieces. Si intersection Sj is empty, 3 mutually disjoint pieces where I will write again these 3 separate pieces. S1 is all those lambdas for which f lambda is not 1 1. S2 is all those lambdas for which f lambda is 1 1, range of f lambda not dense. S3 is all those lambdas f lambda is 1 1, range of f lambda is dense, f lambda inverse is not bounded on range of f lambda. It is defined on f lambda and R f lambda and it is not bounded. These are the three parts. Now, based on the experience in the early days on differential equations etc., that came from physical problems and how the spectrum there looked like, certain names were given for this, and this is called the point spectrum. This is called the residual spectrum, and this is called the continuous spectrum. Of f for the operator f. So, the point spectrum of f, residual spectrum of f, and the continuous spectrum of f. Particularly the names point spectrum and continuous spectrum was because of the experience that these category 1, they were like eigenvalues of a matrix, discrete. There were certain points on the complex plane, and the continuous spectrum was like a band, the word continuous. Okay, so there was a whole band which belonged to that, whole patch belonged to in the complex plane that belonged to that. But however, subsequently when we construct pathological examples for operators, you can construct operators for which the point spectrum is a band and the band spectrum is a point. So, in the early days it was called band spectrum because of the physics, okay. But actually the band spectrum was point and point spectrum is band. You can concoct examples like that, but sometimes historical mistakes in naming remain, okay. My friend Professor Tikekar, who used to always tell in the class, Sulochana, a girl, does not mean she has beautiful eyes. Okay. So, the name was a mistake, historical mistake. Maybe the child would have probably will later turn blind. So, unfortunately, the parents named her as Sulochana and the name doesn't change. Like whatever you can do, like that in mathematics also, there are names like rational numbers and irrational numbers, real numbers and imaginary numbers. There is nothing real about real, which is imaginary about imaginary. There is nothing rational about rational numbers and nothing irrational about irrational. The people were thought that they were rational and the other fellow was irrational. In fact, actually it is the reverse. They were irrational and that fellow was rational. So, there were some names which stick. So, these names stick. The point spectrum, the continuous spectrum names stick despite the fact that they really do not reflect reality. Okay. So, now a few simple observations. Okay. So, now what is the resolvent? The resolvent is the rest of the complex plane. Is this for all these lambdas, f lambda inverse is defined as a bounded operator. We will see some real examples of all these things, but first I will put through some theory and then we look at the examples. Okay, some simple observations. suppose you have let us look at the real numbers or the complex numbers. Now, in the real numbers or complex numbers, we talk about sequence of real numbers and their convergence. Then we talk about infinite series of real numbers or infinite series of complex numbers. When we talk about the convergence of infinite series, we convert it to the problem of convergence of sequences by looking at the partial sum sequences. If the sequence of partial sums converge to something, then we say that this series converges to that thing. Analogously, we can do that in a Banach space or even a nonlinear space. Okay, so let us stick to Banach space. So, let X be a Banach space. You can do it in nonlinear space also, okay, but we will stick to Banach space. So, an infinite series x naught plus x1, x naught or x1, whichever way you want to write it, x2, etc., xj belonging to the space, if you have an infinite series, is said to converge to an x in X if, well, I know what is meant by convergence of a sequence in a nonlinear space. So, look at the sequence of partial sums. If the sequence Sn equal to x naught plus xn minus 1, the first n terms of partial sums converges to x, or that sequence is Cauchy. If it is Cauchy in a Banach space, automatically it will converge. So, to show convergence, whenever you are in a Banach space, if you are not interested in the limit but showing only convergence, it is enough if you show it is a Cauchy sequence. Okay. So, we will keep this in mind. That is the first point, that simple observation. The second observation that I want to make is, remember that when we consider the space of all bounded linear operators from one nonlinear space to another nonlinear space, we said if the codomain is a Banach space, the space of bounded transformations will also be a Banach space. In particular, we took the codomain to be the complex numbers and got the functionals and the dual spaces, etc. So, if the codomain is a Banach space, the space of all bounded linear transformations is a Banach space. So, in particular, if I have a Banach space and look at all bounded linear operators on them, that will become itself a Banach space. So, if X is a Banach space, then Bx, the space of all bounded linear operators on X is a Banach space. And therefore, whenever I want to talk about convergence in Bx, it is enough if I show Cauchy. Whenever in a Banach space, to show convergence you need Cauchiness. Since Bx is a Banach space, to show convergence in Bx, I will always show Cauchy. Okay. So, now I am going to look at something very interesting. Let us look at f, which is a bounded linear operator. That is, f belongs to Bx. So, f is a bounded linear operator on X. So, now look at I minus f. I want to look at I minus f inverse essentially. When can I do it? Whether I can get I minus f inverse in a simple form and things like that. Now, to do that, I will do the following. forget about Banach spaces, forget about non-linear spaces, everything. Think of instead of I the number 1 and in f to be a number f. So, I want to look at 1 minus f to the power of minus 1 and I have the series 1 plus f squared plus f cubed etc., and that series will converge to 1 minus f inverse provided mod f is less than 1, the geometric series. Now, that mod role is played by norm. So, if norm f is less than 1, I plus f squared plus f cubed etc. will converge to that. That is what I want to look at. So, we shall show that if norm f is less than 1, then the series I plus f squared plus etc. converges in Bx to I minus f inverse. So, that means I minus f inverse is a bounded linear operator and this series converges to I minus f inverse. Analogous to geometric series, there is this geometric series version in the space of all bounded linear operators. Now, before I come to this, okay, let me, so how do we show? Similarly, we had another 1 plus f. What is 1 plus f? 1 minus f plus f squared minus f cubed. So, that is also true if norm f is less than 1 and I minus f plus f squared minus f cubed converges to I plus f in Bx. Let us take this for granted for the moment, we will prove it in the next class. So, I will see what I am aiming at. So, these two geometric series converge under the condition that norm f is less than 1. Okay. That is first observation. Then we will make many observations. Suppose f belongs to Bx, that is f is bounded operator. F is a bounded linear operator on x and suppose f inverse exists. Let me put a capital F so that suppose f inverse exists in Bx, that is a bounded inverse. Suppose I have a linear operator which has a bounded inverse. Okay. So, I have a perfectly genuine bounded linear operator whose inverse is also a genuine bounded linear operator. Now, what I will do is I am going to look at any g in Bx, consider any g in Bx, some other bounded linear operator. Then I can write g as, let me see, f plus g minus f, that is no problem, right, f plus g minus f. Now, f is invertible, so I can pull out an f and write it as I plus f inverse into g minus f, right. It is like what we do in matrices. Okay. So, since f is invertible, it has a bounded inverse, I can pull out that f out and that f inverse will go to that. Now, this fellow has an inverse, that is what we have assumed. Suppose this fellow also has an inverse, then the product of the inverse is the inverse of the product in the opposite direction. Same story holds as in matrix theory, same proof also holds. So, therefore, if that fellow has an inverse, then G also has an inverse. Okay. So, let us call it as K. If K inverse exists, then G inverse exists and G inverse is equal to K inverse F inverse. The inverse of a product is the product of the inverses in the opposite direction. So, therefore, now let us go and see when does K inverse exist. So, when does, so let us look at when K inverse exists. Okay. So, now that 3 says if this fellow has norm less than 1, remember I plus F inverse exists if norm F is less than 1. So, if I plus something inverse exists if that something has norm less than 1. So, by 3 K inverse exists if norm of F inverse times G minus F is less than 1. But when you have two bounded operators, the norm of a product is less than or equal to the product of the norms, because each is controlling one elasticity. So, that is if norm of F inverse times norm of G minus F is less than 1, because then that will be less than this and this will be less than 1. That is if norm of G minus F is less than 1 by norm F inverse. Now, how can I put 1 over norm of F inverse F? What if that norm F inverse is 0? If norm F inverse is 0, then F inverse must be 0 operator. But if it were 0 operator, it could not have inverse in the first place. So, therefore, I am assumed that the fact that F inverse exists, that F inverse is not a 0 transformation. So, if F inverse is not 0 transformation, I can put this. And therefore, what does this say? All this says is that anything in Bx will have an inverse provided it is close enough to F. Okay. So, let me write this. So, F has an inverse. So, F inverse exists. Let me call this F, let F inverse exist. Okay. Let F delta be equal to 1 by F inverse. Then the set of all G in Bx such that the distance between G and F is less than delta, that belongs to all G belongs to this, implies G has inverse. G inverse exists, G inverse belongs to Bx. What does that say? Every invertible operator has a neighborhood, every member of him who is invertible. That says the set of all invertible operators form an open set. Everybody has a, so let us call this, so let I, this is what? This is simply the open ball of radius delta about the point F in that space. Okay. What is this? The set of all those fellows who are within a distance of F, within a distance of delta from F. So, therefore, let I be the set of all invertible operators in Bx. Then F belongs to I implies there exists a delta positive such that B delta F belongs to I, which implies I is an open set. So, the set of all invertible operators is an open set. See, in matrix theory is very easy to, even here it is very easy to see. In matrix theory, what does that mean? If it has to be invertible, the determinant must be positive, the determinants must be not 0. So, the determinant is a continuous function on the matrices, and the set of all, if a continuous function this is not 0 at some point, there is always a neighborhood in which it is not 0. It has to be either greater than 0 or less than 0. If it is greater than 0, then the neighborhood is greater than 0, less than 0, the neighborhood is less than 0, that is an open set, at least in the real case. Complex case is little similar. So, therefore, that is exactly what this result says. Whenever you have an invertible, the collection of all invertible operators, they form an open set in Bx. Okay. So, now what we are going to do is, the time is up. So, what is our plan? We have the complex plane. This complex plane has been split into two parts. Given a bounded linear operator, we have split the complex plane into two parts. One is the spectrum and the other is the resolvent. Each is complement of the other. Using these ideas, we will show that the resolvent is an open set in the complex plane, and therefore, the spectrum must be a closed set, being the complement of it. And we will see that there is a very particular structure, a particular circle in the complex plane. The entire spectrum has to be contained within that. So, it is not only that the spectrum is closed, but it also has to be bounded. The spectrum is a bounded closed set. It has to be within. So, actually what is that? If f belongs to Bx, you draw the circle of radius whose norm f, okay, then the spectrum lies within this circle. The spectrum lies within this circle, and this optimal circle is called the spectral radius. The smallest circle which encompasses, outside which no spectrum lies, is called the spectral radius, which is a very important number for even in the matrix case. That is the modulus of the largest eigenvalue. What happens in the matrix case? There are only a finite number of points in the spectrum. Choose the largest fellow and draw the largest modulus fellow, draw the circle. So, that is the modulus of the largest modulus of eigenvalues. That is called the spectral radius of the matrix. Okay. Anything beyond that is comfortable zone. They are all in the resolvent, inverse problems are not there, and so on and so forth. Your problems will all be within this, and these tell you everything about that. This is the beauty. Okay. The spectrum tells what is about the resolvent in this problem solving. Okay. So, there is a peculiar kind, because this fellow is not that. So, not that also has an information about that. Okay. So, if you want to know what is not that, you must know what is that, or if you know what is not that, you know that. If you know that, you know what is not that. That is the logic. Okay. So, there has to be an interlink between this. So, therefore, these bad points which have problem about defining inverse have information about good points. So, without knowing who is bad, you do not know who is good, and without knowing who is good, you do not know who is bad. So, the important thing is that we can trap the spectrum inside an optimal circle in the complex plane. The radius of that optimal circle will be called the spectral radius. So, we will look at all this in the next class.